Module 1. Unit 1. Introduction to Quantitative Analysis. Quantitative analysis is a fundamental approach to decision-making that relies on mathematical and statistical techniques to analyze data and make informed decisions. This approach involves the systematic application of quantitative techniques to understand and solve complex problems. Quantitative analysis is a scientific approach to decision-making, as it involves the logical and rational evaluation of data to derive conclusions. It is distinct from qualitative analysis, which focuses on non-numerical data and subjective assessments. The primary goal of quantitative analysis is to use numerical data to make objective and reproducible decisions. This approach is particularly useful in business and economics, where decisions often need to be based on measurable and quantifiable data. One of the key components of quantitative analysis is the use of models. Models are simplified representations of real-world situations that help analysts understand complex systems and predict outcomes. In quantitative analysis, models can take various forms, such as mathematical equations, graphs, or computer simulations. These models are used to analyze data, test hypotheses, and evaluate different scenarios. For example, a break-even analysis model helps businesses determine the point at which total revenue equals total cost, indicating no profit or loss. This point is known as the break-even point and is crucial for making informed financial decisions. The three categories of business analytics, descriptive, predictive, and prescriptive analytics, play a significant role in quantitative analysis. Descriptive analytics involves analyzing historical data to understand what has happened in the past. This type of analysis helps businesses identify trends, patterns, and anomalies in their data. Predictive analytics, on the other hand, uses statistical techniques and machine learning algorithms to forecast future events based on historical data. This approach helps businesses anticipate future trends and make proactive decisions. Lastly, prescriptive analytics combines data analysis with optimization techniques to recommend the best course of action. This type of analysis is particularly useful in decision-making processes where multiple alternatives need to be evaluated. Computers and spreadsheet software are essential tools in quantitative analysis. They enable analysts to perform complex calculations, visualize data, and build sophisticated models. Spreadsheet software like Microsoft Excel is widely used for its versatility and ease of use. It allows users to organize data, perform statistical analyses, and create graphs and charts to represent data visually. Additionally, specialized software packages like SAS, SPSS, and R provide advanced capabilities for statistical analysis and modeling. While quantitative analysis offers many benefits, it is not without challenges and potential problems. One common issue is the quality of data. Accurate and reliable data is crucial for meaningful analysis, but data can sometimes be incomplete, inaccurate, or biased. Analysts must carefully evaluate the quality of their data and take steps to address any issues. Another challenge is the complexity of models. While models can provide valuable insights, they are simplifications of reality and may not capture all the nuances of a situation. Analysts must be aware of the limitations of their models and use them appropriately. Implementation concerns are another important consideration in quantitative analysis. Even the most accurate analysis can be rendered useless if it is not implemented effectively. This includes ensuring that the results of the analysis are communicated clearly and that decision-makers understand and trust the recommendations. Additionally, organizational factors such as resistance to change and lack of resources can hinder the implementation of quantitative analysis. In analyzing a problem, it is crucial to study both the qualitative and quantitative aspects. While quantitative analysis provides a data-driven approach to decision-making, qualitative analysis offers valuable insights into the context and nuances of a problem. Combining both approaches can lead to more comprehensive and informed decisions. Quantitative analysis is a logical approach to decision-making because it relies on systematic methods and objective data to draw conclusions. It is also considered a rational approach because it involves the use of reason and logic to evaluate alternatives and make decisions. By applying mathematical and statistical techniques, quantitative analysis helps ensure that decisions are based on sound evidence rather than intuition or guesswork. One of the key concepts in quantitative analysis is the break-even point, which is the point at which total revenue equals total cost, resulting in zero profit. This concept is crucial for businesses as it helps them determine the minimum sales volume needed to cover their costs and start generating profit. By calculating the break-even point, businesses can make informed decisions about pricing, production levels, and cost management. Unit 2. Decision analysis. Decision analysis is a systematic and analytical approach to decision-making, which involves understanding and evaluating the factors that influence the choices available to decision-makers. At the core of decision analysis is the identification and definition of decision variables. Decision variables are the controllable aspects of a decision-making problem. For instance, in a business context, decision variables could include the amount of inventory to order, the price of a product, or the allocation of resources. Understanding these variables and how they can be manipulated is essential for making informed decisions. In decision theory, probabilities are associated with states of nature. States of nature represent possible future conditions that can impact the outcome of a decision, but are beyond the control of the decision maker. For example, market demand, weather conditions, and competitor actions can all be considered states of nature. By assigning probabilities to these states, decision makers can better assess the potential risks and benefits associated with different choices. If probabilities are available to the decision maker, the decision-making environment is referred to as one of risk. In such environments, decision makers use probability distributions to evaluate the likelihood of various outcomes. This allows them to calculate expected values and make decisions that maximize expected utility. For instance, expected monetary value, EMV, is a common criterion used in decision-making under risk, where each potential outcome is weighted by its probability and the corresponding payoff. Decision trees are a valuable tool in decision analysis, particularly when dealing with complex decisions involving multiple stages or branches. A decision tree is preferable to a decision table when an EMV is calculated because it visually represents the sequential nature of the decision-making process and the associated probabilities and outcomes. Decision trees help decision-makers map out possible choices, the states of nature, and the payoffs or costs associated with each combination of choices and states. One of the key metrics in decision analysis is the expected value of sample information, EVSI. The EVSI equals the EMV with sample information, assuming no cost for the information, minus the EMV without sample information. This metric helps decision makers determine the value of obtaining additional information before making a decision. If the sample information is perfect, the efficiency of the sample information would be 100%, meaning that the additional information completely eliminates uncertainty. When assessing utility values in decision analysis, it is essential to understand the concept of utility. Utility represents the subjective value or satisfaction that a decision maker derives from a particular outcome. In assessing utility values, the worst outcome is given a utility of 0, providing a baseline for evaluating other outcomes. By assigning utility values to different outcomes, decision makers can compare them more effectively, even if the outcomes differ in nature or magnitude. The decision-making process involves several steps that guide decision-makers from problem identification to the final choice. These steps include defining the problem, identifying the decision criteria, generating alternatives, evaluating the alternatives, selecting the best alternative, and implementing the decision. Each step is crucial for ensuring that the decision is well-founded and that all relevant factors are considered. Decision-making environments can be categorized based on the level of uncertainty involved. The three primary types of decision-making environments are certainty, risk, and uncertainty. In a certainty environment, the outcomes of all alternatives are known with certainty. In a risk environment, the probabilities of different outcomes are known, but the actual outcomes are not. In an uncertainty environment, neither the probabilities nor the outcomes are known, making decision-making more challenging. Techniques for making decisions under uncertainty include the maximax, maximin, and minimax regret criteria. The maximax criterion involves selecting the alternative with the highest possible payoff, focusing on the most optimistic outcome. The maximin criterion involves selecting the alternative with the best of the worst possible payoffs, focusing on the most conservative outcome. The minimax regret criterion involves selecting the alternative that minimizes the maximum regret, focusing on minimizing potential losses. Bayesian analysis is another important tool in decision analysis, particularly when new information becomes available. Bayesian analysis allows decision-makers to update their probability estimates based on new evidence, leading to more accurate and informed decisions. By revising probability estimates using Bayesian analysis, decision-makers can incorporate new data and insights into their decision-making process, improving the overall quality of their decisions. The importance of utility theory in decision-making cannot be overstated. Utility theory provides a framework for understanding and quantifying the preferences and values of decision-makers. By assigning utility values to different outcomes, decision-makers can evaluate choices based on their overall utility rather than just monetary value. This approach is particularly useful when decisions involve trade-offs between different factors, such as risk and reward, short-term and long-term benefits, or personal and organizational goals. In decision analysis, decision variables are the elements that decision-makers can control to influence outcomes. Understanding and manipulating these variables is crucial for optimizing decisions. Probabilities are associated with states of nature, representing the likelihood of different conditions that affect decision outcomes. When probabilities are available, the decision-making environment is one of risk, allowing decision-makers to use probability distributions and expected values to guide their choices. Decision trees are valuable tools for visualizing and analyzing complex decision problems. They help map out choices, states of nature, and associated payoffs, making it easier to calculate expected values and identify optimal decisions. The expected value of sample information, EVSI, measures the value of obtaining additional information to reduce uncertainty, while utility values provide a way to compare outcomes based on subjective preferences. The decision-making process involves a systematic approach to identifying and evaluating alternatives. Different decision-making environments, certainty, risk, and uncertainty, require different techniques for evaluating choices. Bayesian analysis allows decision-makers to update probabilities based on new information, while utility theory provides a framework for evaluating choices based on overall satisfaction or value.